Well, hello everyone. This is Scott Roberts from Explore Scientific and the Explore Alliance, and I'm here with Dr. Daniel Barth. And today, on this 48th episode of How Do You Know, Dr. Barth will talk about and help us understand more about the Hubble constant. Daniel?
Hey, Scott. Thanks for hosting again, and it's exciting to be here with our audience for our 48th How Do You Know program.
Right.
Very exciting. We'll go ahead and jump right in. I've been out playing with astronomy equipment again this last week. We had some nice clear skies. So I've been experimenting with a combination of red dot and green laser finder on some of my astronomy equipment. I have a red dot finder. I don't have an Explore reflex finder yet. That's on my list.
Not yet. I got them in stock, so I'll make sure you get one.
That's on my list. I'll have to get one and review it. But right now I have a red dot finder, typical of what you see them on a lot of hunting applications and stuff. It's in astronomy applications. It's a classic red dot with a lens and a reticle you can change. And the thing I found is that the red dot is mounted so low to the barrel that when I'm looking through the red dot, the barrel of the telescope obstructs the view of the sky. And so when I'm looking for a bright target like Jupiter, Saturn, or a bright star, I'm looking for a double star. It's fairly easy to put the dot on the star and I'm there. But when I'm star hopping to find deep sky stuff, and then I find that the barrel of the telescope is obscure part of the sky for me. And so I've been exploring with a green laser finder, a green laser pointer that I can mount on the same rail. And it's kind of an over-under thing because I can see the red dot over the top of the green laser apparatus, and I can turn the laser on and just point the telescope and say,
the general part of the sky. How accurate is it with your green laser?
It's quite accurate. I can go ahead and put it on. I can put it on like, let's say I was out looking at Antares the other night and some of the Messier objects around it, and I can put the green beam on Antares and leave it on, and I look through the eyepiece and I see the green beam on Antares, and the unit I have is accurate enough that I can take it on and off of the rail, and it doesn't lose its alignment.
Maybe
so
a couple
I can take it off.
Sounds pretty accurate. Maybe a couple of arc minutes, maybe.
Yeah, I would think. I haven't actually measured it. And it's one of these where it's like a lot of the red dots. It's got a little Allen screw where you put an Allen wrench in and adjust it. And I usually set these things on Polaris because it doesn't go anywhere. And I find when I zoom it in and when I go ahead and look on Polaris, I can get it accurately enough that even at 5 power, I can put the green beam on a star or an object and have it in the field of view easily. So it's working great and it's lots of fun. I still want to get an Explore reflex sight and try it and take some review it for our audience. So I saw that last time I was up at the studio, and Kent Marsh was showing them off, and I'm going, "What the heck is this?"
I gotta have one, 2 of them maybe.
So it's very exciting. So anyway, some opening comments. Something that is not exactly space science, but it's kind of related. The U.S. has regained the supercomputer title, and I saw this ad. U.S. now has first exascale supercomputer. And I'm like, what the heck? Exascale is 1,000 trillions. They said quintillion. It does 1 quintillion floating point operations per second. So it does 1,000 trillion calculations a second. And I was looking at this thing, I was stunned. Has 700 petabytes of active storage. That's 700 million gig. And I look at these statistics and I just crack up. It has 9,400 CPUs and 37,000 GPUs, and it's got more than 8 million core. You know, oh, I've got an 8-core laptop. I have an 8 million core supercomputer, which to me is
Oak
just
Ridge
amazing.
National Laboratory. I'm not surprised.
Yes,
I'm not surprised.
And
Yeah.
they have, it's divided into 78 cabinets, each of which are about 16 by 8 by 5 feet. It's just, and the thing that stunned me, they said, oh, we have to actively cool this. And I'm thinking, well, of course you do. You can't just rely on air cooling. 6,000 gallons, that's 24,000 liters of water. And they circulate it with 4 350 horsepower pumps. And I'm like, oh my God. And I was trying to think about fire engines and go, gee whiz. Well, how powerful are the water pumps they put? I wasn't able to look that up. I'm thinking they have like the power of several fire engines circulating water all the time to keep this thing cool. Just astounding. And Scott, you know we've done the million, billion, trillion thing here on the show, where we give people kind of an idea. We say, oh, okay, $1 million in $100 bills weighs 10 kilos. You can put it in a big backpack or a gym duffel bag, rucksack. And if you get $1 billion, it's about a 2.5 meter cube of money. It weighs 10 metric tons.
Wow.
$1 trillion in $100 bills covers a football, either American or European, football field from end zone to end zone, sideline to sideline, 2.5 meters deep, 8.5 feet deep. And if you want a quintillion, you need 1,000 football fields. And that comes out to something crazy like 1,500 acres. It's about 2.5 square miles stacked, 8.5 deep with $100 bills. And we now have a computer that does this many operations per second.
So is this computer self-aware yet, or, you know?
Well, you know, I'm thinking that one of the things they would want to try on it is some of these simulations where you say, ooh, let's simulate a solar system assembling itself from a cloud of 1 billion particles of gas and dust. And you just set it going and you program gravitation and heat and compression and radiation factors.
5 minutes later, it gives you your answer.
It gives you your answer and says, oh, here's a solar system with 8 planets and 2 asteroid belts or whatever. I think it's going to be just fantastic, especially given we're going to be getting better data from instruments like the Webb and the Roman Space Telescope when that comes on. And they're going to be plugging this data into computers like this to help make sense of galaxy formation, dark energy, dark matter, expansion of the universe, all these things. And I think about this technology, and Scott, in our lifetime, somebody sent me an ad and they said, oh, here's what computers were like when you were in college. And they showed an ad for like the Osborne. You know, it's 45 pounds, the size of a suitcase, but you can take it with you. It has a 5-inch screen and 48K of RAM.
It had a screen.
That's right.
Right.
And 5.25-inch disk drives. And so, you know, it was only $5,000. Which in today's money is
$10, right?
No, then dollars, about $50,000 now.
Oh my gosh.
Something I wanted but could never afford. And
yeah,
we look
I think
at,
my parents' house cost something like $7,000 or $10,000 back.
We have now, you know, smartphones, and my little Surface laptop, which is like a Gen 4 Surface, and it has an i5 processor and all this crazy stuff. But then you look at this thing and you realize, like, the cutting edge is, oh my gosh, it's so far out there. It's fantastic. The other exciting news from the week is the Maven spacecraft lives. And this was very exciting. Maven, Scott, is the Mars Trace Gas orbiter. And it's looking at atmospheric data on Mars. It's been up
on the
there
rover,
for
right?
9 years.
Maven lives on the rover. It lives on Perseverance, correct?
No, this is an orbiter.
Oh, it's orbiting. Okay.
This is an orbiter. It was there
Okay.
9 years ago. So what does that make it? 2013, it went into orbit, and
Okay.
it's been orbiting and analyzing the gases. And that's the orbiter that was looking at things like methane plumes on Mars and other fun stuff. And it went into safe mode, and they were afraid that it was going to spiral out of control and be lost for good. Because what happened, they launched it with inertial guidance, package of 3 gyroscopes,
Okay.
and by how the gyroscopes are positioned, because of course the spacecraft orients itself, but the gyros don't move. And so they were using inertial guidance to tell them where they were. Well, the first one failed, and they brought the backup online because, of course, it's NASA. They have a backup, right?
Sure.
The astronauts, the early astronauts didn't have backups, but the new spacecraft do. And the second one was going wonky too. And so they were like, oh my gosh, we're going to lose this. And they were able to switch and create and upload software that now lets Maven get its position through cameras by stellar positions. So they're able to upload. A lot of us have used things like Stellarium and Starry Night, and where we get a view of the sky, they're able to take pictures from their camera and compare them to software package of the sky and determine where they are in their orientation. And they still have the inertial guidance, and apparently there are some functions where it still relies, it's locked into the inertial guidance package. And so they're saving it. They're saying, we have inertial guidance number 2, and we're only going to turn it on when we really, really need it. But they've given the software. You realize this thing was given a mission expectancy of 1 year. It's been up there 9 years now. NASA is famous for this. Oh, the rover will last 90 days. Oh, it's up there for 12 years. Now, NASA builds. I want my next SUV built by NASA. I'm sure it would cost more than my life is worth. But I want a like a Hyundai 10-year warranty, but I want it running in 2130.
Right.
10 or 12 times the expected warranty lifetime. So anyway, Maven is up and running, and there's a picture of it, and it's quite lovely. And it's very exciting. And there's a link to learn more about Maven, of course, in the show notes, which I hope everybody will download. So let's go ahead, and these next 2 shows, this show and next week, are going to be about the Hubble Constant mystery. And NASA stirred the pot a couple of weeks ago, and they used the clickbait word. There's something weird going on in space. Tune in soon, NASA blog. Well, what they're talking about is something that we've known about for a long time, which is the Hubble Constant mystery. And we're going to take this week's show, and we're going to learn about the Hubble Constant and why it's important. And then next week's show is going to be dedicated to the mystery and where we're going to solve that. But for this week, we're just going to talk about the Hubble Constant and Edwin Hubble a bit. And because we realize that our show, Scott, is not a show for experts. It's a show for everyone. And so there are times when I can talk to you, and you and I can have a conversation. Scott, have you heard the latest news? And you'll say, yeah, sure, that's really cool. And then I think about it, and I realize,
obviously, I didn't
our audience.
Yeah.
And a lot of us this week, yeah, I know already, Doc. Come on. But let's be courteous for everyone so everyone starts on the same page. So who the heck was Edwin Hubble? He was the guy they named the Hubble spacecraft, the space telescope after, but why get that honor? Well, he was the American astronomer who first established 2 great things. One is that the universe is expanding, and the second is that the universe goes beyond the Milky Way. He established that the spiral nebulae in the sky were in fact island universes, which was the term of art in the 30s. We say now they're galaxies, and everybody says, well, of course they're galaxies. This was not always known. And Hubble, there's an image of the fellow himself. Handsome guy. He has hair. Good for him. Hubble was interested in all of this and he wanted to do astronomy. And then the United States got involved in World War I. And so he really quickly finished his dissertation. He wrapped up his dissertation and submitted it. And then in the United States Army in World War I, he rose to the rank of major. I've not been able to track down what he did. So maybe it was really exciting and secret. I'm not sure. But when he came back, it turned out that George Hale, he actually applied for a job. The 100-inch Hooker telescope was coming online at Mount Wilson. And there was a job open for a researcher and research director for the Hooker. And Hubble, is that his draft card? His Army, and the American Expeditionary Force. Yeah, Major. It looks like Major Infantry. I doubt they risked him in the infantry, but very cool. He went and served his country, so salute to Major Hubble. But when he applied for this job and he said, "Oh, Mr. Hale, I'd love this job, but I've just enlisted." And Hale said, "We'll hold the job for you," which a stunning act of both good sense and patriotism on the part of Mr. Hale. A lot of men and women go off to serve in the armed forces today, and they come back and they hope there's a job waiting for them. And there are companies that do hold jobs or promise reemployment, and good for them. And Hale said, "You know what? Best man for the job. We're going to hold the job for you." And it turned out to be a brilliant decision on Hale's part. Hubble came back, and with the brand new, shiny 100-inch telescope, can you imagine? You come back from the service and somebody says, "Here you go. We've got it, the dome, the telescope. It's been all commissioned. It's tuned up. It's tracking. It's aligned. It's the largest in the world. And now, what would you like to look at and explore?" Oh my gosh, such exciting times. Well, he took a look at Cepheid variable stars. Cepheid variable stars, friends, are stars that are used as what we refer to as a standard candle. In other words, part of the idea are these spiral nebulae, separate galaxies. Well, the question was, how far away are they? We thought at that time the Milky Way was about 300,000 light years wide. So if they're closer than 300,000 light years away, they're structures inside our own galaxy, much like globular clusters. If they're substantially farther away, then you go a long way to making the case that these are independent galaxies somewhere out in space. So to do that, you have to find out how far away are they. The idea of a standard candle, if you have a standard candle, something where you know how bright it is, how many lumens, how many photons does it put out, you can go ahead and measure its apparent brightness. How bright does it appear to be in my telescope? Compare the absolute brightness to the apparent brightness, the old inverse square law, thank you, Isaac Newton, and you can go ahead and write it accurately. Turns out Cepheid variable stars, their brightness is precisely determined by their period. They cycle up and down, very bright to very dim. They have a range. The period with a telescope, and once you know the period, you know the absolute brightness. The physics behind this is very solid. And so with the new 100-inch Hooker telescope, Hubble was able to measure and identify Cepheid variable stars in Andromeda. That was his first target. The closest galaxy. How do you know it's the closest? It's the biggest in the sky. The full extent of Andromeda, it stuns many people. Andromeda is about 2.5 degrees wide. So it's about 5 times larger than the full moon in the sky. And when we look at it with an amateur telescope, we're generally looking at the bright central core and bulge. But in fact, if we had a very large telescope, we could see Andromeda, and it's gigantic. And so we knew it was close, so he could identify Cepheid variables. And from that, he said, oh, well, look, 2 things are interesting. First of all, the distance for Andromeda comes out to be a couple of million light years. And he looks at this and he goes, wow, a couple of million light years away. That's astounding. That's many, many times, with our Milky Way galaxy being about 0.3 megalight year. Andromeda is about 2.5 to 3 megalight years, Hubble's measurement. And so you go, wow, it's 10 times farther away than our galaxy is big. Obviously, wow, this is outside of our galaxy. And Hubble continued to take data from about 23 nearby galaxies. And he found out every time he looked at a spiral nebula and got a distance for it, it's very far away. And so Hubble joined the ranks of Copernicus and Giordano Bruno and many scientists. Ah, there it is. Isn't it lovely?
Yes.
Oh my God. And it is not, as I think I'm correct, this telescope is not designed for optical use at all. It's strictly an instrument for.
Although I will point out to you, Daniel, that they do visual observations for it today, and
Okay.
They use an Explore Scientific ED-127 as kind of a relay lens so that you can get an eyepiece on the scope. This is the only way that you can actually look at the 100-inch mirror, is with one of our telescopes. So we're real proud of that.
That's awesome. Now, do they mount that up in the cage near the ED-127 up near the front?
Actually mounted it behind the primary mirror, and so there is a. So they're
using the Cassegrain focal point.
They have, right, and so it's tons of magnification, as you might imagine. So the telescope is aimed at a couple of flats, which then, so the light's coming in from the 100-inch mirror, hits a flat, hits another flat, runs down through a tunnel to the ED-127 telescope. So
that's astounding. That's
I love it.
Astounding. And I use a couple of Explore Scientific 127s in my astronomy program, and they are just superb instruments. So I'm going to be like, wow, and this is what we use for a primary imaging system on the hooker. That's right. Awesome. That's stunningly cool, because I knew it wasn't designed initially for visual use.
And in October, we will take people to go look through the 60-inch up there. So I've already kind of posted the link on there. You might want to go to that.
I want to go. I'm going to find a way.
Okay. I know a guy.
My dogs. Start selling one of my dogs. You hear that, buddy? My dog Parker is here at my feet, and he's about 100, and he's close to 50 kilos now.
Oh,
so he's he's a big kid.
Dog.
Yeah, he's only 14 months, so he's not fully grown yet. He's just a. Anyway, so Hubble, you realize, Scott, there's been a whole history of people who said, no, the universe is bigger than that. You go back to the old geocentric system. The Earth is in the center. The sun orbits us. The moon orbits us. All of the planets orbit us. We are the center of everything. Beyond Saturn is the celestial sphere of the stars. And beyond that, of course, is where God, where heaven is. One of the reasons Copernicus was really held with great contempt by members of the early Catholic Church is that Copernicus said, no, every star is a potential solar system, and the universe is thousands of times bigger than we thought it was. And Copernicus kind of said, no, we're really a very small place in a very big space. And Giordano Bruno, of course, came in and went one step further. I'm sure Copernicus thought this. We have no evidence for this, but how could he not? Each star is a sun. It's home to other planets. And Giordano Bruno said, there's not just the Earth, there are many worlds and many suns. And he said, I'm sure God blessed them all with life. And so he was kind of the first guy to say panspermia and spontaneous generation of life. And they burned him at the stake in May of 1600 and for heresy. He wasn't well connected like Galileo, who also said he did the experiment with his telescope, and he said, by the way, I can now prove to you that the Earth is not the center, that it's the sun, and we are a solar system, not a geocentric system. And so this lent weight to the arguments of Bruno, who was by then some years dead. And so, wow. And from the time of really Galileo, early to mid 1600s, we have Newton and we have Kepler, but they're mostly focused on how does our solar system work, gravitation, the mechanics of orbiting planets. And then we go forward a couple of centuries and we hit Hubble, and Hubble says, wait, the Milky Way is not the entire solar system. Kant, Immanuel Kant, the German philosopher, was one of the first people to say, oh, the Milky Way is actually a giant disk of stars with a bulge of stars in the center. We get Laplace of the formation of both stars and galaxies. But everybody said, oh, but the Milky Way is it. The Milky Way is the universe. And so now we've expanded from, one star solar system to, Galileo's telescope shows him thousands of stars. Bruno said they could all be solar systems. There might be a few thousand solar systems. And then Kant and others come along, Laplace and others come along and said, no, it's the whole Milky Way. There could be many millions of stars. Understand at that point that large barred spiral galaxies like the Milky Way are hundreds of billions of stars. And now Hubble comes along and says, all the spiral nebulae are Milky Ways. They are all galaxies. They all contain potentially billions of stars. So, and he is measuring things out to many tens of mega light years. And so the universe takes this giant expansive leap again. And as Hubble continues investigating, one of the things he's finding is the new Hooker telescope, great big monster that it is big enough to actually take the spectra of a galaxy. Now, we've been taking spectras of stars for going on for a century. At that point, we're talking circa 1920s. And Hubble says, ooh, now I can photographically record a spectra. To get a spectra, Scott, you're going to take from a source and put it through either a prism or a diffraction grating and spread it out into the rainbow of colors. And Fraunhofer, Bunsen, and many other scientists from Germany in the 1850s and 60s were taking spectra of elements, and they were looking at the spectra of stars, and there's the mystery of the dark lines in the solar spectrum. And it was Fraunhofer who said, oh, these are matching up to the same spectra we find when we vaporize elements in a laboratory here on Earth. These dark spectra must be absorption lines of vaporized elements in the sun's atmosphere. And they go, ooh, look, this collection of lines is oxygen, this one's hydrogen, this one's nitrogen, carbon, et cetera, et cetera. And they go through and they identify all of them that they can, and then they come up with one that's quite strong, and they say, oh, we don't have a match for this. And they called it helium, after the god of the sun. And so helium is discovered first on the sun, not on the Earth. Fascinating story. Well, the thing is, when you... Sorry, go ahead.
No, I said that is fascinating because, I mean, we use helium to blow up balloons with. And so I wonder when that, kids started playing with helium.
All helium on Earth comes from the radioactive decay of uranium, and it's trapped in buckets underground and is mined like natural gas. So it's an interesting and limited resource. So you go ahead and you've got these spectra. Well, when you take the light of a star and you spread it out of a sufficient width through a prism or a diffraction grating in order to get a spectrum, then what you're doing is you're taking the point light from a star and you're diffusing it over a very large area to get that spectrum. Well, okay, fine and dandy, but when you want to do that with a galaxy which is millions of light years away and a very dim object, of course, our astrophotographers are all with us right away to get an image of a deep sky object which is far away, number one. Number two, it's a diffuse object. It's not a point object. It's spread out in and of itself. And third, it's a very dim object because it's really, really far away. Well, the answers are two, I need a bigger imaging mirror or objective lens. Aperture fever, every astronomer knows that one. I want a bigger telescope. And then you start plotting ways to save up for it. And of course, Hubble had a 100-inch, that's what, a 2.5 meter diameter mirror, which is just amazing. So with the Hooker telescope, you have a 100-inch mirror, and you're talking back in the 1920s. They did not have the option that most astrophotographers do today, which is to collect a series of images and then use software to stack them. They could not do this. So what they needed to do was take a photographic plate and expose it and have very precise tracking. And they didn't have electronic tracking aids at that time. So it amounted to an astronomer sitting with a coaxial telescope and, putting a crosshair on a star and adjusting the tracking of the big telescope to keep the crosshair centered.
And it was hard work, and it was cold, and back in those days at Mount Wilson, you had to wear a suit and tie.
Oh, yes. Oh,
suit and tie all night long for hours and hours guiding on this crosshair. Crazy.
My students complain when I send them to the classroom and I say, gentlemen need to wear a button-down shirt and tie. Well, can I wear a polo shirt? Can I wear a Razorback t-shirt? No. Dress like a professional. Oh, you're mean. I'm like, you have no idea. Yeah, so it was a suit and tie environment, and I'm imagining he had a parka over that. At least I hope he did, because some of those nights on Mount Wilson can be very cold. And he's sitting there manually adjusting the tracking for hours. And then they would cover the plate sometimes and go back and get more hours of exposure the next night. Clouds came in or whatever, they wouldn't just say, oh, throw the plate away. No, they would reset everything the next night, collect more photons. So getting a spectrum on a galaxy was weeks of agonizing, grinding work. And no computer technology at all to help you. This is all doing calculations by hand, slide rule. And Hubble managed to get spectra for 23 nearby galaxies. The interesting thing he found with all the spectra is all the spectra were redshifted. And now we get into Christian Doppler and the Doppler effect. We all experience a Doppler effect most often when we hear an emergency vehicle with a siren, like an ambulance or a police car, and it's coming towards us, and we hear the characteristic wah, and the tone starts out high, and then it drops as it goes past us, and we're experiencing Doppler shift. If you're a fan of NASCAR racing, or you just hear a very fast car go roaring past you, you hear the same thing. The pitch of the engine is very high when it's approaching, and then it drops significantly as it goes past, because on the approach, the waves are blue shifted, the wavelengths are compressed, and the frequency is higher. And when the object is receding from us, the frequency, whether you're talking sound or light, makes no difference, is red shifted. That is, the wavelength increases and the frequency drops. Well, a spectrum measures wavelength precisely. And so Hubble noticed, oh, I'm getting all these spectrums. Look, there's helium, there's hydrogen, there's calcium, oxygen, nitrogen, whatever. But he's noticing all the spectral lines are redshifted. And he realizes, as Doppler proved in the 1800s, that indeed redshifting is a precise way of calculating velocity. And since the speed of light is well known, you can use redshift to say, how fast is this galaxy moving away? Now, Hubble, we know, expected some redshift or blue shift. If you think about it, the idea that galaxies just sit there in space and do not move, well, they're subject to gravity. That just doesn't make sense. And so Hubble expected, oh, well, some are going to be moving toward us, some away from us. In fact, Andromeda was the only blue shifted galaxy. All the other galaxies he measured at greater distance shifted. And it turned out, and there's a nice, I think I have, I do, and we're going to try this. Here we go. We're going to share this screen. There we've got a nice image. And this is Hubble's diagram for type 1a supernovae. And he's measuring with type 1a supernovae. He's using them as a standard candle. And he's saying, okay, here's our standard candle. This gives us a distance. Redshift from the spectra gives us a velocity. What the heck? Let's plot the two together. He notices, gee, it seems like the farther away they are, the faster they're moving away from us. And he gets this lovely little diagram here. And he thinks about this. You can imagine getting this data. You can imagine getting this data, Scott. And you're looking at this and you're saying, wow, okay, goodness, I've got this data and my little screen is showing black here. I'm hoping that I'm back on. I stopped the share. Anyway, I don't know. In any case, maybe I'm on the wrong. Boy, I don't know. I'm just going to assume that our good friend and producer, Paul Newton, has me back on.
Are you trying to show the Hubble diagram?
I did show the Hubble diagram, and then I turned sharing off. There we go.
Oh, it's off now. It's off now.
Okay, so I'm seeing myself. New sharing software friends. So there's always it's live. It's a live program.
It's a live program.
Oh, there you go. There we go. We've got the image of the show notes from Mr. Newton side by side with me. Great. So Hubble says, well, look, all these, there's obviously a relationship between distance and velocity. And you think to yourself, well, there's two possible interpretations here. One, Copernicus was wrong. We are the center of the universe, and the universe is expanding, and everything is expanding from us.
Yes.
But I don't really held on to that idea for very long. What's known as the Copernican principle. The Copernican principle says that if your data seems to show that you are in a privileged location, time, era, or anything else, you're wrong. You're interpreting it incorrectly. Copernicus says, no, the Earth is the center of the solar system. The sun is. The sun isn't the center of the cosmos. There are many stars. And Bruno said, yes, and there are many worlds. And on we go, and we find out that we occupy no special place. The Copernican principle has been upheld in every field of science for 400 years. And so I can't imagine Hubble said, ooh, we're special, at least not for very long. But you think about it a little bit and you go, what could be the other answer? And the other answer is the whole universe is expanding. And when we talk about that, I often get a question when I share this idea the universe is expanding, and people say, oh, so it's like a balloon that's expanding inside a room, right? And there's this giant space, and our universe is expanding into it, and that's not right. Space is expanding. And people get frustrated with that. How do I even imagine that? And the best way I can share with you is an example, an analogy called the raisin bread analogy. Think about if you're making a loaf of raisin bread. So you have dough, flour, egg, water, whatever, and then you have some yeast in there, and you knead the raisins into the dough, and they're evenly mixed in, and then you allow the dough to expand. Well, if you measure the position of any particular raisin, as the dough expands, it's getting farther away from every other raisin. And it doesn't matter which raisin you test. One in the center, one at one end, the other end, one on the surface, one on the interior. It doesn't matter. You can do the same thing at home if you take a regular child's toy balloon and you take a permanent marker and you mark a series of dots all over, and you measure the uninflated balloon. How far apart are all the dots? You can number them and plot them, and then you go, okay, let's go ahead and blow up the balloon a little. We've got our dot number 1, which is where we're considering to be the Milky Way, and we measure the positions to all the other dots. And we realize the farther around the balloon we go, the more the distance has expanded. Why? Because it's the latex fabric of the balloon that's expanding. And every square millimeter of latex fabric in between the two dots is being stretched as the balloon expands. The same thing is true with the dough from our raisin bread example. Every cubic centimeter of dough is expanding. And so we realize that, oh, it's space-time that's expanding. And as it expands, as the dough carries the raisins, as the expanding fabric and envelope of the balloon carries the dots we drew on it, we find that, oh, yes, the whole fabric and volume of the universe is expanding, and it carries the galaxies and star systems along with it. And like the dots on the balloon, we are ending as we get stretched and pulled. And so Hubble's constant is how much expansion do we get per unit of distance? So you think about it, it's like the two spots on the balloon. If they're farther apart, the rate at which two dots on the balloon move apart depends on how much latex fabric is in. And you could measure millimeters of expansion per unit distance, per unit time. And so this is what the Hubble constant is. And this is a cutting edge and very controversial piece of science, and he publishes a paper on this in 1929. A lot of people are like, nah. I get the same reaction when I teach astronomy, and I say, oh, and by the way, the universe is expanding. Well, you don't really mean that, right? Well, how could it, if it's the whole universe, how could it expand? And you get all the same questions that Hubble got in 1929. Hubble's great discovery, you think about this. You think about Copernicus, you think about Galileo, you think about these great astronomers. And kind of like them, Hubble is not actually honored by the scientific community with their top dedication. No Nobel Prize for you, Edwin Hubble. It turns out that in the 1920s and 30s, they didn't consider astronomy to be a legit part of physics. For physics, but rather like mathematics, astronomy is kind of the redheaded stepchild of the Nobel Committee, and there's no prize for astronomy. Apparently, Mr. Nobel didn't consider it worthwhile or didn't think of it, or maybe he didn't know any astronomers. I don't know. The rumor is that he never gave a prize in mathematics because a mathematician philandered with his wife at one point, so he said, no mathematics prize. I don't know if that's true or not. Maybe. completely apocryphal. But there was, in any case, no prize for astronomy. And Einstein said, please, you must give this man a Nobel. Sandage, Eddington, many Nobel laureates and prominent scientists and physicists said, look, Nobel Committee, this is the whole damn universe is expanding. What more fundamental thing could you possibly imagine? But he never received a Nobel Prize, and he died relatively young in 1953. And nope, no Nobel Prize for you. Now, interestingly, we know that Wilson and company got the Nobel Prize for the cosmic background noise. In many other ways, by many other parts.
Yeah, you're freezing up just a little bit there, Daniel. And I have questions to ask you if your connection improves. So let's do this the old-fashioned way. I'll call you. Oh, there you are.
We could do them.
Are you back? Okay,
Yes.
so we have some questions here, and Pekka Hautala's got at least 4 questions here. So let's see if I can get back to question number 1. Maybe his first question was, when is the proper time to ask some questions? Okay, every time. So
Now.
let's see. Now,
All the time.
Lots of comments back and forth. Let's see. People had comments about early computers and early software operating systems, et cetera. Let's get all the way down to Pekka's first question. Lots of comments. Probably have 100 comments. Let's see. Mike Wiesner hopes to see you at Mount Wilson in October. So,
Yes. Gosh,
yeah.
I hope
Question
so.
1. Here we go. Can we detect rejecting light, photons? Can we detect rejecting light? I'm not sure what that means.
I'm not either. We can
Maybe
image
reflecting
galaxies.
light. I don't know.
Reflecting light?
Reflecting light, yes, of course.
Your reflection nebula, we can detect out to several tens of thousands of light years. I'm certain, for instance, from Andromeda. So,
well, if I'm interpreting it correctly, he says, can we detect rejecting light, photons? If yes, why can't we calculate those photons that have passed and are older than 13.8 billion years? Does that give you any insight to this question?
You can't determine the age of a photon. The particle is timeless. And quite literally, and there's all sorts of relativity theory reasons for that, but let's just take it as read. Photons are timeless and do not change and do not decay. So when we get a photon, it does carry information. It carries wavelength information and frequency, and we can get intensity. And from spectra, which is a collection of photons, we can get information about composition. And from redshift, we can get information about the relative velocity and travel of the source of those photons. The photon's motion imprints information on it, and the source of the photon's temperature and position imprints information on the photons, just like the motion of Allen's information on the sound coming from the siren. So all information comes to Earth, but what that does not come to us is the age of the photon. From 13.8 billion years ago, the era of recombination, when the universe is transparent. That photon is indistinguishable from a LED in the room with you. So photons, we can't directly say how old they, nor do we have any kind of like radio dating. We can look at them and wait from radioactive decay and isotope ratios how long it's been since then solidified, but we have no way to a new tool for what we call our distance ladder. How do we measure things at different distances in space? Can redshift take over the whole light wave spectra in a long time? You do get increasing redshift as things are farther away. The structure of the spectra itself, let's say the arrangement of the lines, how far apart they are, etc., this remains invariant. So the spectra from a distant galaxy, although it's shifted to the red and the lines appear in a different place on the red, orange, yellow, green, blue, indigo, violet spectrum, all the lines appear in place, the intensity and the difference in the structure of the set of lines remains unchanged. And so if changed, that would add one more variable. It would be really difficult to measure velocity then. So that the spectra themselves remain invariant, but their position on the spectral grid, if you will, shifts, and that's what we measure. Can nebulosity exist outside of a galaxy? Yes, certainly. We see this when we look at, say, M51, the Whirlpool galaxy, and we see this light bridge that extends, and we know that, oh, there's a companion to M51, and a streamer of stars is being, and gas is being stripped off. And the light we see is stars that are being formed, but it's also partly the nebulosity from these stars that are being stripped, which are exciting the gas, which is being carried along. We can see glowing streamers of gas from the large and small clouds. And we can detect, and that nebulosity is beyond our galaxy. To some extent, when you're looking at that sort of data from a distant galaxy, it's not really possible to sort out the glow from the nebulosity from the glow from stars. It's all light at that point, all spectra information, but it's a matter of brightness and angular resolution. If we're going to say the Orion Nebula, and it appears to be a certain number of minutes of arc wide, well, we project that type of a nebula out onto the galaxy of Andromeda. Now it's a couple of million times farther away, and so it becomes vanishingly small, a pinpoint object in even the largest of telescopes, like the Hale, the 5-meter Palomar telescope, or the James Webb Space Telescope. They just don't have the resolving power to see something like that. We can identify individual stars out in the halo of galaxies. This is how we see Cepheid variables and type 1a supernovae in galaxies. But again, something like the Orion Nebula is a diffuse object. It's not a bright pinpoint of light. Its brightness is spread over, and so from that distance, it's really not visible. With an 8-inch aperture f6 Dob, will I see the Veil Nebula visually?
Yes.
Wow, that really depends on the Bortle quality of your sky.
Yes, it
I
does.
think you get Bortle 3 or below. The answer would probably be yes. I live in a Bortle 3 region. You can go out to the American Southwest, West Texas, Arizona, Nevada, the Rocky Mountains,
Panhandle of Oklahoma. Yeah.
Right, the Panhandle of Oklahoma. You can go out to some of the islands in the Pacific, and certainly you can get that quality of skies where the answer would be yes. But if you're in a more urban area, no. You can still do it photographically, but again, that relies on collecting photons over time. And your eye is an instantaneous visual processor. Your eye does not collect photons. It would be fascinating if we had that biological capability, and it might be possible, but there's no real evolutionary need for it, so it's never been seen in a biological organism.
Could you detect a
Can you
region
detect
of
a region of space expanding faster or slower than baseline? That's a real interesting question, and they're building new telescopes to look for dark matter and dark energy to answer just some of those questions. We know that Vera Rubin was able to detect non-Keplerian rotation, so motion that was atypical. So in principle, I would say the answer would be yes. We could measure galaxies which defied or weren't falling nicely along the Hubble constant line. But to my knowledge, nobody's found anything that violates the Hubble constant yet. Now, we're going to take that up in next week's show because there are different kinds of measurements which give different numbers for the Hubble constant. And one of the questions, the big questions in astronomy today is, why is that true? Why, when we measure with different instruments, do we get a different number? And all of astronomy and physics would like to know, how do you reconcile these measurements? Ideally, if the Hubble constant is a thing, we should be able to measure it any way we want, with any measurement we wish, and we should always come up with the same data. Some people propose, and I'm teasing this week, some people propose that the Hubble constant hasn't been the same all the time. Some people are proposing that the Hubble constant isn't the same everywhere. Other people are just saying, you know, we're not wise enough in the ways of physics and astronomy and instrumentality to determine why we're getting a discrepancy. And so that's something we'll be tackling next week. So thank you for the teaser straight man question. Do we have any more good ones? These are all great.
No, somebody wants to know, what are the odds of other life forms looking like humans existing out in the stars? I believe aliens exist. If it happened here, maybe it happened some other place, but you can't throw odds at that, you know. So
yeah, it's very, very hard. It's very, very hard. You talk about there's a large evolutionary advantage to be either radially or bilaterally symmetrical. In other words, radially symmetrical like a starfish or an octopus, or bilaterally symmetrical like almost every invertebrate and vertebrate that exists. I'm trying to think of the octopus is the only, but it's an invertebrate. I can't think of any vertebrate that is radially symmetrical.
Yeah.
There may be one. That would be, someone else says, what part of the wave is being observed? It's actually a wave front. It's a wave front. If you have the light wave coming into Earth like a surf coming into the beach, the whole wave train is coming at us. And when we open our telescopes, when we take the cap off, when we peer in, we're just catching that first part of the wavefront of an ongoing wavefront. You think Andromeda is 2.5 million light years away, so the light has been on its way for 2.5 million years, and Andromeda has been visible in our sky for millions of years. So that train of light, that wave train, has been impacting on the Earth that entire time. And we're just get a particular part of it when we point our binocular telescope and we go, wow, cool, Andromeda. Or last night the other night I was looking at M13, the Hercules globular cluster. I'm going, wow, this is great. I'm seeing this beautiful fuzzy cluster and I'm going, this is amazing, this is lovely. And I'm realizing, yes, that has been for tens of thousands of years. I think Hercules is something like 30,000 light years away. Off the top of my head, don't hold me to that.
That's
But so those photons have been on their way for 30 millennia, and they were destined, fated, chance. They came down my optical tube and into my retina. Bang, there it is, and I'm showing. Wow. So it's fun to think of these things when you're out observing.
right. With M13, it's 22,180 light years, give or take. Give or take some number, right?
Something I would like to throw out to our audience. I have an alternate plan, but I would really like 50 to be an audience participation episode. I would like folks from our audience to send in questions to Explore Scientific or to me at astronomyforeducators@gmail.com. Hey, Doc, it's Ask Doc Anything show. If we don't get enough good questions, and you guys have loads, I can't believe if you don't put your mind to it, you could all submit 2 or 3 and we could have a whole show easily. But if not, I have a plan B, but I would like for our 50 to make it, let's answer audience questions. Those photons didn't travel for nothing, says Pekka. Yes. I don't know if a photon's ambition would be to activate a rod cell in my retina and make me go, wow, killer cluster. But certainly that would be the effect.
Maybe that's the reason why we have rod cells, is to collect,
collect those photons. Indeed. There's my email, astronomyforeducators@gmail. And Scott or Paul will put up a link for the Explore Scientific email. Let's send in some questions. Yep. Let's send in some questions, and wild and crazy as you like. Make it very speculative. Make it about where do you think we're going with space exploration and travel? What's the fate of manned space exploration? Are we going to put boots on Mars? What do you think about the Drake equation, life elsewhere? I'm going to throw it wide open. Martian meteorite. Let's try to avoid really wacky conspiracy theories. But apart from that, I will pretty much take on all comers. If we really have a bunch of people who want me to tackle flat Earth type questions, maybe we can have a whole show on Dr. Barth debunks conspiracy theories, which might be a fun show to do. I know Scott and I would get a giggle out of it. But,
right.
For this 50th
for the 50th episode, Peck has one last question. In fact, I think he probably has more questions than this, but we'll make this the last question, Pekka. Has theory of universe like multidimensional funnel been tested, considered as a potential model? I mean, light spread out and falls back to funnel as Big Bang.
Is the cyclic universe hypothesis?
Yeah, like the Big Crunch, right?
Right. What makes it sound like bang crunch, bang crunch, bang crunch? The universe for a very long stretch of time. The idea that the universe would expand for a time and then fall back in, or alternatively, it actually comes from Asimov, Isaac Asimov, the science fiction writer. Everything falls into black holes, all the black holes, and then they evaporate spontaneously in a new Big Bang. And he did a science fiction story on that, The Last Question, something like that. And Freeman Dyson, American physicist, calculated something called the golden age. And he calculated how long will it take for all of the black holes in the universe. If everything falls into a black hole, all the black holes coalesce, how long will it take that ultra mega jumbo black hole to evaporate from Hawking radiation? And it's like something like 10⁻⁸ power. It's just a mind-boggling number. And if you go, it's the biggest number in science. And if you go look up age, it's a stunningly big. The shock absorbers on my brain just crashed trying to imagine this, because we talked about the amazing exascale computer, which is 10 to the 10th, something like that, operations per second. And now we're talking about 10 to the 180th power. It's just, and I would love to see the calculations on that. I would love to see the calculations on that. Freeman Dyson was a very imaginative thinker. He of the Dyson sphere, right? Build a metallic sphere around a star and thereby capture all of its energy, and it gives you virtually unlimited area to colonize and live on. It's kind of an interesting idea. There are people who are looking for Dyson spheres because they would have a particular signature.
I see. Yeah.
And again, that's been science fiction fodder. Larry Niven and the Ringworld books talk about this idea related to a Dyson sphere. So there you go.
Crazy.
My head's full of junk.
Okay, so
yeah, our audience to mine this. Give us some questions.
Yeah. So you guys, you're coming with lots of questions now. Okay. Josh and Harold and everybody else that's got more questions, Pekka, write them down. Okay. Put them in the email, and we will answer these on a future How Do You Know? Okay. So
episode 50.
They'll try to stump Dr. Daniel Barth and see where we can go with that.
Yay.
But, okay, I think that's going to wrap it up for today. Daniel, thank you so much for spending your hour with us. And and that's going to be a wrap. Thank you very much to the audience, and you guys have a great Monday evening, and we'll see you tomorrow. We do have the 96th Global Star Party happening, and so with special guest will be Kelly Beatty from Sky and Telescope Magazine. So looking forward to it. Take care.
Bye-bye now.